You know, inside every single high-performance battery, there are literally thousands of tiny connections, all forged by welding. And the quality of those little bonds, it dictates absolutely everything. So today, we're going to break down the 3 core welding techniques that are really the unsung heroes of battery tech. We'll look at how making the right choice here is the difference between a top-tier EV battery and a major safety hazard.
So here's the plan. We'll start with the big challenge every battery engineer has to tackle. Then, we're going to dive into what makes ultrasonic, laser, and resistance welding so unique. After that, we'll put them head-to-head to see how they stack up. By the end of this, you'll have a really solid framework for picking the absolute best process for whatever you're building.
And this is really the whole game right here. It's so much more than just sticking 2 pieces of metal together. We're talking about creating a bond that has the lowest possible electrical resistance, the highest mechanical strength, and is just rock-solid reliable. And you have to do all of that without frying the sensitive components that are just microns away. Seriously, every single decision you make at this stage sends ripples through the entire system, affecting performance, safety, and how long that battery is actually going to last.
All right, let's kick things off with our first method, ultrasonic welding. Now, as the name kind of hints, this technique is your go-to when you need a really delicate touch, especially when you're trying to join 2 different kinds of materials.
The absolute key thing to understand about this method is that it works without melting. Think about that. Instead of turning metal into liquid, it uses super high-frequency vibrations to literally scrub the surfaces clean at an atomic level. This lets a true metallurgical bond form while everything stays solid. It's this solid-state magic that makes it perfect for joining tricky, highly conductive things like the thin aluminum and copper foils you find in a pouch cell.
So how strong is it really? Well, the final strength all comes down to a precise recipe of weld time, vibration amplitude, and clamping pressure. When you dial those in just right, you get incredible shear and peel strength. And that is absolutely critical for surviving the rough life inside an EV battery pack where you've got constant vibrations and temperature swings trying to tear weaker bonds apart.
Electrically, this is where ultrasonic just shines. Because you're not melting anything, you're not trapping impurities or creating tiny voids in the weld. The result is an extremely low, and this is the important part, a very consistent contact resistance. What that really means for the battery is less energy wasted as heat, which directly leads to better efficiency and a longer life.
That low heat input is also a huge win for reliability. You're not cooking the delicate separators or electrolytes right next to the weld. And with no molten metal splashing around, the risk of causing an internal short circuit pretty much vanishes. What you're left with is a solid-state bond that has fantastic structural integrity, which is vital for the stability of the whole pack.
Okay, so now let's switch gears and contrast that with our second method, laser welding. If ultrasonic is all about that delicate, solid-state bond, then laser welding is about surgical precision, raw power, and incredible speed. And that's exactly why it's become a powerhouse in high-volume manufacturing. So unlike ultrasonic, lasers do melt the material, but they do it with this incredibly focused beam of light. This creates a really deep, skinny weld with a teeny-tiny heat-affected zone, or HAZ as we call it. And because it's a non-contact process, it's perfect for high-speed robotic automation. It's the reason it's become the standard for welding terminals and bus bars on cylindrical cells at a massive scale.
When it comes to pure, brute strength, laser welds are just formidable. They give you incredibly high mechanical strength, which makes them the obvious choice for joining the bigger, beefier structural parts of a battery. The final strength all comes down to a finely tuned dance between laser power, the focus of the beam, and how fast you move it across the material.
And what about the electrical performance? Well, a perfectly controlled laser weld creates a super clean, uniform fusion zone. It's free of voids, free of impurities. The bottom line is you get extremely low contact resistance, which is exactly what you need to push huge currents through bus bars and terminals without losing a bunch of power.
The reliability here really comes from that precision. That minimal heat-affected zone means you're not messing with the properties of the metal right next to the weld, which lowers the risk of it becoming brittle and failing down the line. For demanding, long-life applications like an EV, this level of structural integrity isn't just nice to have, it's a critical safety requirement.
All right, last but not least, let's talk about the industry's classic workhorse, resistance welding. This is a mature, well-understood process that's been reliably building strong connections for decades.
The principle behind it is actually pretty simple. You just clamp 2 pieces of metal between a pair of electrodes, you blast a massive electrical current through them, and the metal's own resistance to that current flow generates a ton of heat right at the contact point. This melts a little bit of material, which then cools and fuses into what we call a nugget, and that's your weld.
So the strength of a resistance weld is all about the size and the quality of that nugget. And you control that with three things: weld time, current, and the force you apply with the electrodes. But there's a trade-off. That direct contact means the electrodes can actually leave little dents in the material, which is a geometric thing you have to account for in your design.
Now pay attention here, because this is a really crucial point. The electrical performance can be all over the place. The process actually relies on the initial contact resistance to even generate heat in the first place. So any little variation, a bit of dirt on the surface, a slight change in pressure, can change the final weld quality. A bad weld means high contact resistance, which can create hot spots and waste a lot of power.
So while it is a reliable process overall, it's definitely not as precise as a laser. The heat-affected zone is usually bigger, which means it's often a better fit for more robust components like cell tabs and connectors that aren't quite as sensitive to heat. Getting the process control right is absolutely key to avoiding problems like splashing that can mess up the joint's integrity.
Okay, so we've looked at each one individually. Now for the fun part. Let's pull them all together and see how they really stack up, side by side across our most important criteria.
This table really lays it all out pretty clearly, doesn't it? You can see right away how laser just dominates when it comes to raw strength for those thicker materials. But then, look at ultrasonic. It excels with that shear and peel strength you need for delicate foils. And then, for the electrical performance, which is so critical, you can see that both laser and ultrasonic give you that superior consistency that's just tough to guarantee with resistance welding.
So, what's the verdict? Which one is the best method? Well, the truth is, the answer isn't in the welding technique itself. It's all about the specific job you need it to do. And this slide just nails that point perfectly. Let's say you're joining a bunch of layers of thin, dissimilar foils inside a pouch cell. Ultrasonic is the no-brainer choice. Its low-heat, solid-state process is exactly what you need. But what if you're welding a thick copper bus bar to a terminal on a cylindrical cell? Now you need the raw power and precision of a laser to get that deep, reliable connection without overheating the whole cell. And that's really the key takeaway from all of this. Picking a welding process is always a complex engineering trade-off. You're constantly balancing the need for flawless electrical conductivity with the demand for rock-solid mechanical strength, all while juggling the real-world pressures of manufacturing speed, cost, and automation. So we'll leave you with one final thought to put all this into practice. Imagine you're faced with this exact engineering challenge, a high-powered bus bar that needs to be incredibly strong and electrically perfect. Based on everything we've talked about, which process are you going to choose? And more importantly, how would you justify that choice? Because getting that answer right is what builds a better, safer, and more powerful battery.